In this video, we're going to be covering the solution to the problem entitled Yet Another Problem About Sequences from the January 2019 Long Challenge from CodeChef. The problem states for a set of positive integers s, let's define GCD of s as the greatest integer which divides each element of s. If GCD s equals 1, the set is called coprime. For example, the set 7, 12, and 15 is coprime, but 6, 12, and 15 is not coprime since every element in the second set, this set, is divisible by 3. Your task is to find an integer sequence a0 to an-1 such that the following holds. For each valid I, the element ai is between 1 and 10 to the 9. a0 to an-1 are pairwise distinct. For each valid I, the set ai, ai plus 1 modulus n is not coprime. The percentage denotes the modulo operator. And for each valid I in the set ai plus 1 modulus n, ai plus 2 modulus n is coprime. It is possible that there is no solution. If there are multiple solutions, you may find any one. And the constraints for this problem are that the number of test cases we're going to get, t is between 1 and 1,000, and the number of elements that we are asked to generate for each of these test cases, n is going to be between 3 and 50,000. So this is quite a confusing problem statement, but after looking at the examples that CodeChef provides us with, it's a little bit more clear. So let's take a look at those. So here is the example input and the example output. The first number 2 is the number of test cases we're going to get, and then we have two numbers that follow. 3 is the number of elements that it asks us to generate for the first test case, and 4 is the number for the second. And it provides us with two examples that we can use to get a passing solution for these inputs. And it also provides us with explanations, which is fantastic. So let's read those. So for example case 1, it says, let's check the answer for GCD 6, 10 equals 2, so the greatest common divisor of 6 and 10 is 2, which obviously is the case. GCD of 10, 15, which are the second and third elements, is 5, and then the GCD of 15 and 6 is 3. But that the GCD of all three elements is equal to 1. So every two cyclically consecutive numbers are not coprime, but every three cyclically consecutive numbers are coprime. So it's basically asking us to construct a sequence where each of the adjacent elements have a GCD greater than 1, but each of the three adjacent elements have a GCD equal to 1. So in other words, they're coprime. And note that one of the trickier parts of this problem is that it's not just for the adjacent elements in the array, but also it wraps around. So you need to make sure that the last element and the first element are not coprime, but that the three elements that sort of span around, so both, in this case it doesn't matter, but if we take a look at 4, so both the two last and the first should be coprime, and the last and then the first two should be coprime. And we won't walk through the second example, but if you want, you can pause the video and verify that each of these numbers, for the adjacent ones, they have GCDs greater than 1, and for three consecutive or adjacent elements, they have GCDs all equal to 1. So hopefully that makes sense now what we're trying to solve, and this is a pretty interesting problem. I've got some good visuals, hopefully, that will help you understand how to solve this. So a big part of it is using sort of these first three numbers to generate sequence. So basically what we're going to do is we're going to figure out how to generate a list of 50,000 of these, making use of prime numbers. And then every single time we're given a test case, we're basically just going to output the first n elements of that pre-computed vector or array, and then we're going to do something special for the last couple elements to make sure that it wraps around. So let's take a look at just how we would go about generating that array, the pre-computed vector of 50,000 elements that satisfy these coprime conditions. So here we have the first three elements from our first example in our test case, and what I've done is in the first line I've shown the elements, or the values of the elements, and then in the next two lines shown the factors that make up this value. So clearly 6 is equal to 2 times 3, 10 is equal to 2 times 5, and 15 is equal to 3 times 5. So note that these are all prime numbers, and we sort of have a pattern here where we can see that We have 2 2s, so these are the factors within these two elements that make them not coprime. And then for the second and third, we have 5 and 5. And then also the 3 and 3 here make it, when you wrap around, that 15 and 6 are also not coprime as well. But when we look at all 3 of them together, they don't all share a single common factor. So if we just take this and we continue to extend this out by taking a new prime when we need it, we can do the following. So we have a 3 here, so obviously we want to fill in a 3 here. And in order to make this sort of not common, and remember that one of the conditions was that these numbers have to be pairwise distinct. So if we've seen a 6, 10, and 15, we can't have a 15 or 10 or 6 here. So if we fill a 3 in here, we can't use 2 and we can't use 5, so the next prime would be 7. So 3 and 7 makes 21, and we've now got, we're still satisfying our coprime condition for the moment. So if we continue to extend this, we fill the 7 in over here. The next prime that we can use is the 5, because 5 hasn't been paired with 7 yet, so we get 35. Continue to do this, and it'll look as follows. Fill the 5 in, take 11, 55, fill the 11 in, take the 7, 77, fill the 7 in, take the 13, get 91, and so on and so forth. And so we're going to continue to do this up until 50,000. And there's one thing we need to do whenever generating our actual output, is that in order to make sure that this wraps around so that we have our first and last element not being coprime, we have to always make sure that we replace one of the factors in our last element with the 3 here. So the way we're going to do that is just basically look at the last 2 elements in our list, figure out what the GCD is, so what the common factor is here, and divide that out of 187. So that would give us 17, and then basically we're going to replace the 17 with the 3. So that is neat, and you might be thinking, okay, that's great, but how do we generate that sequence? Well, if you look at what we're actually doing, how we get these numbers, take a look at our primes. Oh, so that was just an animation to show replacing the 3. If we take a look at our primes, if we take what are the elements that we start with? 2 and 3. So we've got a 2, we've got a 3, and then as we move along, we're basically just incrementing, if we consider these indices, one at a time. So when we move to 2, 5, we just move the 3 and make it a 5. And then to move to the next one, 15, that's 3 times 5, so we move the index pointing at 2 to 3. To get to 21, we replace the 5 with 7. To get to 35, we replace the 3 with 5. And we continue to do this, and basically that's it. So we just have 2 indexes, and we're going to increment them one at a time. So for each iteration while we're looping and generating this sequence, we're just going to have 2 indices, and after the first step, we'll increment the second index, and after the second step, we'll increment the first index. And the only other thing we then have to worry about is when the primes get so big that we risk going over 1 billion, because that was one of the other conditions for our sequence. It said that all the elements in our sequence have to be between 1 and 10 to the 9. And the trick here is that we can make use, or basically repeat this algorithm, and then just make, so when we hit a value above 1 billion, we can reset our indices to point back to the beginning, and then just basically increase the distance between them. So right now, we always have, either one space between them or they're exactly adjacent. So all we need to do is basically kick out this green index so that they always have 2 or 3 for the second sort of implementation or run through of this generation, and then kick it out again so that it's 4 and 5, and so on and so forth. And the way you can think about this is that on our first path of generating these, this shows sort of the primes that get paired together. So 2, 3, and then 2, 5, 3, 5, and then 3, 7. So we're always pairing these primes together as follows. But we're missing out on all these combinations of the primes in this top right corner of our grid. So once we get to the prime values that are close to, I think, 32,000, when you multiply those by each other, you're going to get roughly 1 billion. So as soon as we hit the point where we're going to go above 1 billion, we just want to reset our prime indexes back to the beginning and set one to be equal to 5 or 7, and then set the other one to be equal to 13 or 17, so that we can get these combinations as well. And every single time we go above 1 billion, we just reset these and sort of readjust our indexes that we're using. So hopefully that makes sense. We'll take a look at the code, and that should clear things up if there's any sort of doubts that this might work at the end of the day. And there's also something to note. It says in the solution that output, -1 if you're not able to generate a sequence. That's sort of a red herring, because all sequences you're able to generate up to n being 50,000. So I'm not exactly sure why they put that in. That's sort of mean in my opinion, but c'est la vie. So let's take a look at our code. So we're only going to have a C++ solution for this, and this is the main function that's doing all of the work. So at the top, we're generating primes. We'll look at that in a second. We're just using the sieve of Eratosthenes in order to generate our primes up front. Then we're declaring a vector, which we're going to store our generated sequence in, and then we're initializing some values. The ones we're concerned with right now are I and j. Those are our starting indexes that are going to look into our prime vector here. And then we have a Boolean that we're going to ignore for now because we don't use it in the simple solution. And I've hidden some stuff here that we'll look at afterwards, but we want to just look at the main flow of the algorithm at first. So here's a lambda that basically takes care of our step, and it takes a single parameter, which is either first or second, and based on that, there's slightly different behavior inside. But the main part is the same, and that's calculating the value that we want to insert or push back into our sequence. And we get that by just multiplying the 2 primes that we're currently looking at, and then we just push that back into our vector. And when we see where we're calling these lambdas, we're just looping until our vector or our sequence, generated sequence size is greater than 50,005. I just added a few on after 50,000 to be safe. We're calling step first, and then we're incrementing j, and then step second, and incrementing I. So this is sort of that visualization that I showed before, as we have 2 indices that we're incrementing, one after the first step and one after the second step. And once we've done this, we've basically generated our sequence V, and then we go into output answer, where we're going to read in our T test cases, get n for each test case, and then just output n values from this pre-computed sequence, adjusting the last element, like I said, to make sure that it wraps around correctly. So now let's step into the function. So first we'll look at generate primes, then we'll look at output answer, and then we'll look at sort of the detailed version of the lambda and the while loop here. So first is generate primes. So this is super short. It's a basic implementation of the sieve of Eratosthenes. Here we'll skip over to the Wikipedia animation. So you can see here basically the way this algorithm works is you construct an array up to a certain number, and then you loop through first with 2, then with 3, and then you continue to do it with the primes and basically zero out any number that's divisible by those. And then once you've done that, you go through, and then any number that hasn't been zeroed out, the ones in pink, are the primes. It's a very, very efficient way of calculating them because as you go on, you only ever zero things out that are primes themselves. So if we look at this one more time, it starts with 2, zeroes out everything that's divisible by 2, then 3, and then it's going to skip 4 because that's not prime and go to 5, and then skip 6, go to 7, and then you're left with your primes. So super neat. You can look into this more if you haven't already heard about it, but this is a really good visualization of basically what I implemented. And so now we're back at the code, and this is just basically a simple implementation of that. So note that we are only initializing our vector L here to have a size of 32,000, and that's because 32,000 squared is going to give us a value that's bigger than 1 billion. So we don't need to worry about any primes that when multiplied with another high value prime is going to be bigger than 1 billion, because that is not going to satisfy the constraints of this problem. And so basically we're zeroing out anything that's divisible, that's not a prime, and then once we have that, we just go through, and any number that wasn't zeroed out, we're going to push back into our primes here, and then we just return that. So moving on to our next function, I believe, is the output answers. So if you ignore the first 4 lines here, basically what we're doing is we're just reading in our input n, and then we're outputting the first n-1 elements from our pre-computed vector v. And then for our last element, what we're doing is we're, like I said, getting that GCD and then just replacing one of the factors that we got out with 3. So in the case I mentioned, we were replacing, I think it was 17 with 3. So that's what we're doing here. These 4 hard-coded answers are basically dealing with the case that if you replace a 3, because 3 was used early on, it's not going to satisfy the coprime condition. So the way I dealt with this, it was only, I think, 4 cases that had to be dealt with, is I just manually switched them and then hard-coded them. So there might be a nicer way to do this, but it worked for me. And last but not least is going back to our main function, and we had some stuff that was hidden. So let's take a look at our lambda and our while loop in more detail and see what's going on there. So if we take a look here, we basically were hiding this if condition, which is basically saying if we run into the case where our value is now greater than our maximum. So our maximum here is equal to 1 billion, and note that we also have the step types first and second that get used down in the while loop. So if our value is greater than our maximum, then what we want to do is we want to reset our indexes back to the beginning and then sort of readjust them. So we had declared an A and a B out up front, and that was sort of our reset values for our indexes. So you can see here we're setting I equal to A, J equal to B, and then we're adjusting B for the next time that we reset. So we always want to increase the distance between our indices. And depending on which step we're in, we want to replace one or the other of the indexes and the primes that we're currently looking at. And the reason we have to do this V pushback step here is that when we reset our indexes, we need to make sure that we're still maintaining our coprime conditions. So we can't just reset them without doing anything, because then we're going to not have the GCD greater than 1 of adjacent elements being met. So we're replacing one of basically the current value that we're pushing back. We're using the future index that we're going to reset I and J to with primes A here. And this extra condition here is for when we are in the second step. We want to basically come out of this lambda and then behave as if we are then once again stepping into our second step as well, because this v dot pushback here basically is always going to act as the first step. So if we're in second, we want to set this boolean OK equal to false and then check when we're in our while loop. If OK is not equal to true, then skip the first step and then come into the second step. And the decrement on I and the increment on J is just to cancel out what would happen. So if we're in second and we want to make sure that the next sort of processing of our while loop is second, we need to counteract this increment on I. So we decrement I here, and then we also want to mimic this behavior here. So the increment on J, so we add that here. And then the second time we enter second, after sort of entering this if block and exiting the lambda, we just want to make sure we reset OK to true so that we're not hitting this every single time. So I know that's a bit confusing, but if you want, you can get the code from my GitHub, throw it in a debugger and sort of debug through it. And it makes a lot of sense once you sort of hit the first case where the value is greater than the maximum. So the last thing to talk about is the time complexity of this problem, which, believe it or not, is big O of t times n. And that's because the pre-computation of both our primes and our generated sequence is going to be constant. And that leaves us only with our t test cases of outputting the n elements, which gives us then big O of t times n.
As always, if you enjoyed this video and found it helpful, hit that like button. If you want to see more, make sure to hit that subscribe button. You can follow me on Twitter for reminders 30 minutes before contests start, and you can find all of the code shown in my videos on my GitHub page. Thanks for watching, and I'll see you in the next video.